Good morning and welcome to Unit 2 of STA 220. So Unit 2 is all about different methods of displaying data that we get from a study that we've performed or maybe an experiment that we've performed. And so we're going to start by looking at qualitative data. So what I want to remind you of is that qualitative data is non-numeric data, or we might call it categorical. So it's things like gender, color, race. Right? So things that we don't assign a number to, and there are lots of different ways that we can display our data. So first of all, let's pretend that I gave you a bag of poker chips and they were different colors, and I said, I want you to draw out 20 poker chips without looking, and then I want you to display your results. So first of all, this would be qualitative data because we're looking at the color of the poker chips that you're pulling out of the bag. Color is a categorical variable. There's no number assigned to it. So the poker chips that I have in my classroom happen to be red and white and blue. So that's the three colors that we are going to use. And the first way that you could display your results is with something called a frequency table. So the word frequency means how often something happens. So if I ask you to draw a frequency table, what I'm asking you to do is split your data into classes or categories. And in this case, we have 3. And then to list how many items fell in each category. So let's say that you pulled 7 red chips, 3 white, and 10 blue. That would be your frequency table right there. Pretty easy, okay? You could also present the same data in a slightly different way by telling me something called the relative frequency. So when I do a relative frequency, I'm giving the information as a percent or as a decimal out of the total. So for example, if I have 20 total poker chips and 7 of them are red, the relative frequency I could write as either 35%, or I could list that as 0.35 because those are the exact same thing. Let me highlight my point there. Okay, if I pulled 3 white chips, 3 out of 20 is 15%, or you could list that as 0.15. If I pulled 10 blue chips, that's half, so 50% or 0.50. And there you have a relative frequency table. Okay, we could also represent our data with a pie chart. And I'm going to be honest with you, I am terrible at drawing pie charts. But if I remember what my numbers were, so 7, 3, and 10, I'm going to do my best to draw this proportionally. But with a pie chart, so blue got half. So this side would be blue. And we'd say that was, let's see, blue was 50%. Right? And then we pulled, I believe it was 7 red chips. So that's going to be 35%, which would be somewhere right in here. And we'd say red was 35%. And then for white, I'm not sure it'll let me do white. Let's find out. Yeah. For white, we got 15%. So with a pie chart, what we do is we draw a circle and we attempt, which I did not do a very good job of, but we attempt to split the pieces up proportionally. So if I'm telling you that blue chips are 50% of the overall data, then I want to give blue chips exactly half of that pie chart. If I am telling you that red chips made up 35% of my data, then I would want to put a little bit over a third of the circle in the sector for red chips, okay? And the big thing here is that my percentages need to add up to 100%. If they don't, I've done some of my math wrong somewhere and I need to go back and double check it, okay? Also, when we do a pie chart, we want to make sure that we label what it's for. So maybe we might label it something like percent of 20 poker chips might be our label for that. But we would want to give it some kind of label. Okay? We could also draw a bar graph, and that's something you're familiar with. So with a bar graph, generally our bars don't touch, and we want to label the bottom of each bar with what it represents. And we could draw our bar graph up and down or left and right. It does not matter. Okay, so I'm going to draw mine up and down, right? And so let's say I want my first bar to be blue. I want my second bar to be red, and then my third bar to be white. And then up the side, I'm going to put a scale. And you could count by ones. Since I've got to go up to 10, I'm probably going to choose to, we'll say I'll count by twos. So 2, 4, 6, 8, and 10. And so my blue bar, it's going to go all the way up to 10. My red bar, though, didn't quite go that high. It only went up to 7. And then my white bar only went up to 3. Okay? So any graph like this that is called has bars on it and represents categorical data is technically a bar graph. But if you notice what I did, I listed these options in order from greatest to least. I could have also gone from least to greatest. If I list them specifically in that order, that is what is called a Pareto chart. Okay, so you don't have to list them in order for a general bar graph, but if I say, hey, this is a Pareto chart, you can assume that it's in order. Okay, so those are our options for qualitative data. We have a completely different set of options for quantitative data. Okay. So let's say for quantitative data, I ask you to do something completely different. Let's say I ask you to survey 10 people, and you ask those 10 people the following question. On average, how much time do you spend listening to music every week? Okay, so the reason this question is going to give me quantitative data is because their answer is going to be a number. Okay, well, one way that we can represent quantitative data is, once again, we can use a frequency table. Okay, so we get to decide when we're dealing with quantitative data what our categories are going to be. So it looks like my smallest answer is 5 and my biggest answer is 30. So let's say that I split up my charts like this. So let's say I go, class 1 is going to be from 1 to 5. Class 2 will be from 6 to 10. And then 11 to 15. 16 to 20. 21 to 25. And then 26 to 30. And again, you wouldn't have to use my exact numbers. There's no rule that says what size your classes have to be. What matters is whatever size class I choose, I need to be consistent. So my class width for each class is 4. And what I mean by that is the distance between 1 and 5 is 4. The distance between 6 and 10 is 4. And it's the same for every class. So for class 1, 1 would be called my lower limit. 5 would be called my upper limit. The distance between those two, which is 4, is my class width. And so what I'm going to do is I'm going to list how many people fall in each category, and that's going to be my frequency table. So between 1 and 5, I only have one person, and I'm going to mark these out as I go. Okay. Let's see, the next category is 6 through 10. And it looks like I have, here's one person at 8 hours. Here's another person at 10. So 2 people fell in that category. And then let's see, we had 11 to 15. So there's 1, 2. So 2 people in that category. 16 to 20. We had 1, 2. Okay, 21 to 25, we had 1, 2. And then 26 to 30, we only had 1. Okay, so what would our relative frequency be? Well, relative frequency is a percentage. So in category 1, there was only one person. Well, that's 1 out of 10, which is 10%, or 0.10. Okay. Our next 4 categories all had 2 people. 2 out of 10 is 20%, or 0.2. And I'm not going to list that in the next two boxes, but they would be exactly the same. And then once we get to the end, we have one person again, and that was 10% or 0.10. So I always want to double check my work. My percentages should add up to 100%. Okay? So we could also do exactly the same thing with a dot plot, and a dot plot is exactly what it sounds like. It's a plot with dots on it. Okay? And so what I might do for a dot plot is, again, I get to choose what I count by. And so maybe I decide that once again, I want to count by 5. So maybe over here is 0, 5, 10, 15, 20, 25, and all the way up to 30. Okay, and what I'm going to do is I'm going to put a dot to represent roughly where each person fell. And I can't see everybody on this chart, so I'm going to put a dot on what I can see. So 15 hours would go here, 25 would go here, 10 would go here, 18 would fall between 15 and 20, 30 would go here, 22 would fall between 20 and 25. And let's say that there was an 11th person that I questioned, and they also said 22 hours. Well, then I would just stack that dot on top of the other 22 that is already there. Okay? And so we would want to give this dot plot a label down here at the bottom. So maybe we say average hours listened per week. Something like that, but some kind of title to tell people what we're talking about. Okay? You could also do something called a stem and leaf plot. And so that may be something that you're not overly familiar with. But what we do with the stem and leaf plot is we split into categories of 10. And so our first line in the stem and leaf plot would look like this right here. And so the first number is your tens digit. The other numbers over here are your ones digit. Okay? So for example, let's say that this was my list of numbers right here. Let me scroll back up and we'll make a stem and leaf plot. So a stem and leaf plot would say, okay, I have on my stem side, I do have some one-digit numbers, so my stem is going to be a 0. I have some numbers that fall in the teens, so my stem is going to be a 1. I have some numbers that fall in the 20s, so my stem is going to be a 2. And then I also have some numbers that fall in the 30s, so I'm going to have a stem of 3. Okay? Then I would have my leaves. So my first number is a 5. That's going to fall in the single digit category. So that is the number 05. The number 8 is also in the single digit category. So if I see an 8 in a stem and leaf plot, I would read that as 08 or just 8. My next number is looks like a 10 if I go in order. So I've already got the 1 written. Now I'm going to list the 0. My next smallest number is a 12. I've already got the 1 written in the stem column. I'm going to write the 2 in the leaf column. I have a 15 as well. I've already got the 1, so I write the 5. And then 18, I would put the 8. And that's it for that row. Those are all the numbers that fall in the teens. Then I move on to the 20s category. I have a 20, a 22, and a 25. And lastly, I have a 30. So when you read a stem and leaf plot, the stem is your tens digit, the leaf is your ones digit, and we list, usually we go from least to greatest, but technically you could also go from greatest to least if you chose to. All right. And lastly, we have something called a histogram. And you may be thinking, a histogram looks a lot like a bar graph. And you're right, it does. Here's the difference. With a bar graph, the bars don't touch because each bar represents a completely separate item. Each item is its own category, right? So if you think about those poker chips, one bar was blue, one was red, one was white. With a histogram, the bars do touch. Each bar represents the same type of item or the same type of data, but each bar represents an interval of numbers, okay? So if I were to look at the bar graph that I have pictured here, it looks like we're looking at grades. So maybe these are quiz scores, right? And so the way I would read it is the bottom of the bar graph now, instead of being a category, this bar right here represents the people who scored between a 0 and a 20. And it looks like, if I read the y-axis, there were 10 people, unfortunately, who fell in that category. Notice the next bar, or bin, has exactly the same width. It goes from 20 to 40. So how many people fell in that category? 20. So your y-axis is your frequency, or how many people are in the category. The bottom of the bar gives you an idea of how wide each category is. Okay? And we want to be careful when we choose the size of our bins when we make a histogram. If you make your bins too big, your data is not going to be separated enough for you to really get a picture of what's happening. So for example, if I have a quiz and my possible scores are from 0 to 100, and I say, you know what? I'm going to split my bins into two groups of 50. Well, the problem with that is that's an awfully big range. So you're going to see the people who scored between 0 and 50 as one category, and then you're going to see everybody who scored between an A and an F from 50 to 100 all in the other category, and I'm really not going to get an idea of how many students really made A's and B's and C's and really understood the content. However, if I were to make my bins too small, so maybe I decide each bar is only going to go from 0 to 5, and then from 5 to 10, I'm going to have so many bars that I'm only going to have maybe a couple people in each category, and that doesn't really give me an idea of what's going on either. So I kind of want to go for something in the middle, okay? And so I'm not going to draw a histogram for our data that we just looked at, but you get an idea of what's going on here, okay? So with dot plots and histograms and frequency tables and stem and leaf plots, there are four basic shapes that we tend to see. Not always, but these are the most common that we see in the real world. So the first category that we could see is uniform, and that means that roughly the same number of people fell in each category, okay? You could also see bell-shaped graphs. You could see skewed right, and you could see skewed left. So as a teacher, if I'm giving a quiz, this right here is the graph that I want to see. I want to see something that's skewed left, because what that means is that the majority of people had a high score, and then I had a trickle of people down here who really struggled, right? So what you look for when you're deciding, is this graph skewed left or is it skewed right, is you look for where the tail is. So here's the bulk of the graph right here, right? Here's the tail. That tail is on the right side, so therefore that graph is skewed right. On this other graph, here's the bulk of the people in my graph. Here's the tail. The tail is on the left side, so that graph is skewed left. Okay? This graph right here appears to have roughly equal tails on each side, and everybody's clustered in the middle, so we could call that graph bell-shaped or symmetric. So here's a question. Which shape would best describe our music data? Well, if you think back to that frequency table, almost every category had exactly two people in it. We had a couple categories on the end that only had one person in it, but for the most part it had two. So our graph, if we had drawn a histogram, would have been roughly uniform. Again, not exact. It rarely ever is exact in the real world, but we had almost exactly the same number of people in each category. All right, so the last thing that we want to talk about before I let you go is how to make sure that we're presenting our data in a way that is not misleading. Okay, so I've pulled some questions from your homework. So here's the first thing I would look at. This bar graph right here is misleading. Why is it misleading? Well, if I don't pay close attention, this first bar is only representing 3 hours, right? The second bar represents a time interval of 3 hours, But then when I jump to this bar right here, that bar represents a time interval of 6 hours. So of course there's going to be more crime during a 6-hour period than there is during a 3-hour period. So it's misleading. So on this multiple choice question, you'll see that I marked D. The reason it's misleading is that not all of the time intervals happen to be the same. Okay? Question number 2. When I look at this graphic, it looks pretty good. So each bar is clearly labeled. I know what color it goes with. It gives me a number at the end of each bar to tell me how many objects or how many children fell in each category. Okay. The other thing I want to check is that the bars are proportional. So red is 5, green is 10, and if you look at that, red is half the length of the green bar. So that is a good graph. It's got labels, it's easy to read, there's nothing misleading, there's nothing that needs to be changed. Okay? So when I look at question number 3, okay, they give me some different types of graphs, and we want to choose the one that is not misleading. Okay? So the first thing I want you to notice, okay, when I look at this bar graph here on option B, it's not proportional, right? Or excuse me, the percentages are not correct. So when I look at this first bar, it goes up to, it looks like roughly 50%. The second bar goes up to 90%, and the last bar goes up to 100%. That doesn't make sense because if I add those percentages together, they add up to over 100%, and there's no way that I can have more than 100% of people giving me an answer because 100% is everybody. So that's misleading. Okay? When I look at C, this is a pie chart. The problem with this pie chart is that it doesn't give me any percents. I can kind of guess. It looks like this bottom category down here is roughly 50%, but because they don't tell me, I kind of have to guess. That's not a good graph. When I look at option D, this is a dot plot. First of all, that scale is going backwards. Why would we go down from 49% to 10%? Second of all, there's no label on the y-axis, so I don't even really understand what those dots represent, right? And then why is A a good graph? There are clear labels, first of all. The labels on the bars can be clearly read. The scale makes sense. I'm going up by 10% every time on the y-axis, and it's proportional. So if I look at 10% and 20%, those lines are evenly spaced out, right? So A is a good graph. Okay, so when I look at graph number 4, there's a couple different reasons why it is not a good graph. This is what we call a pictogram, and it uses pictures on our graph. Generally, that is not a good idea because pictures tend to be hard to read. Okay, so this chart right here, first of all, does not have any kind of axis to give me an idea of the scale of what's happening. I don't really know where this graph ends, so I don't know if I'm supposed to read this as the end of the graph where the bottle ends, or if I'm supposed to go up to where the nipple ends, so that's not good. There's no units given whatsoever, and then we also have images, which we generally refer to as chart junk. And chart junk is things that sometimes I think we think that they make our charts cute or pretty, but really they're just hard to read, okay? So we want to stick with things like bars. We want to stick with clearly labeled axes. We don't want pictures on a graph. They tend to just be confusing, okay? And you kind of see the same idea here. This would be another example of chart junk. So we're using pictures. I don't really understand what those pictures even mean, right? There's no clear axis going up and down. There's no scale. It's not a good graph. Okay. So here we have a graph that is called a time series graph. They're not something that you see in this class a ton, but they are something I want you to be familiar with. Which graph is better? So the problem I see with graph B is in the scale. So when you look right here, you don't start your graph until you get to 8.5 versus here, you start your graph at 0. The reason that's a problem is because you are starting at 8.5 on graph B, it looks like there is a huge jump in price for electricity between years '08 and '09, but in reality, what's happening is you didn't even jump a full percent in price, right? Because actually what you went from, it looks like this might be about 9.3%, and it looks like this is 10. You only jumped in price by 0.7 cents. That's nothing, right? But because of the way you scaled your graph with not starting at zero, it looks like a huge increase. That's misleading because you could cause the customers of that electric company to be very upset when actually it wasn't a big deal. The graph on the left, graph A, starts at zero, and you can see, yeah, there was a tiny increase, but it was nothing to really be worried about. Okay, so when possible, we always want to start our graphs at zero. Okay, so of these three charts, which would be the best? So the problem with charts B and C, they don't start at zero, right? And then also chart B does not include a title, and it also doesn't have a label on the y-axis, so that's not good. We're making people guess at what our numbers mean. All right, and lastly, why is this a bad graph? So once again, this is a pictogram. It's very hard to read. I'll be honest with you, I don't really understand. I guess this color right here is supposed to be about half of the credit card, and that's about 49%, but it still just doesn't really make sense. This card back here serves no purpose. It's just chart junk, so this is not a good graph. All right, and that is the end of our Unit 2 discussion. Let me know if you have any questions.